Hi guys, I don't know if you can see me or hear me, but let me know. I am trying several other things to repurpose old assets, and what you're looking at me on here is a camera that was bought to go and visit Alexander Parkhomov and Piantelli in 2015 and was used in some of the glow stick experiments. I think it was used in the Rossi thermal verification experiments. And the reason I want to show you this is that not all cameras are made equal and not all optics are made equal, and this will become important as we move towards the end of this presentation. So can you just let me know if you can hear me first? Can you hear me? Okay, is that 5 times 5? Does that mean you can hear me? I don't know. Okay, excellent. Right. Fantastic. Okay, yeah, so the camera, what I'm showing you is this shows warts and all. And when you're doing science, you don't want to obfuscate the data that's in the imagery. And you don't want to cause all kinds of problems. Now, when you look at the images that and videos that I'm going to share with you in this presentation, there's something you need to bear in mind, that when you look at images on a video, they're not necessarily representative of reality. They may be not, but we must account for whether the optics, the number of lens components in the optics, anything that's between the lens front and the source of the image, and the image sensor, the way the image sensor works, the resolution of the image sensor, and if in encoding there has been some added artifacts added. Now, I understand this because I've been doing imaging for basically most of my career. I was using Commodore Amiga computers in the, well, what was that, the 1980s to produce actual artwork, and I made a professional business of this. And throughout my career, it's been the absolute goal to ensure that every pixel matters, that every pixel is the right color and it is in the right place, and that when it's encoded, ideally you want as minimum compression as possible in your encoding. And this means that the visual that the customer would see as I was looking at it then would be the closest thing to reality. And that goes for when you were simulating reality. You would want to create things that would create the impression of what you would see, for instance, with your own eyes. And your own eyes, they sample at below, I think it is 74 hertz. And so that's why you can see flicker, or it's not a true sense of reality when you're looking at 24 frames per second in film footage. And when you're looking at 30 or 25 in video, or more modern sample rates are 50p and 60p. It's when you get above, I think it's something like 48, you start to not notice. But then when you get above, I think 74, really the eye can't perceive any faster change in imagery. However, within a particular image, there can be artifacts introduced by the way that the images have been sampled and the time that the aperture is open for and exposed to the light source. So you can have some types of cameras can freeze moments in time. So if you had you get these very fast phantom cameras, and if you look at lightning through a phantom camera, some of the best shots of lightning through one of these extremely high speed phantom cameras, you only see a fraction of the lightning and you have no idea what the exact shape of the lightning is until the ball lightning has made the discharge channel, and then you get the full discharge, which is appears to be more instantaneous. You can see these little traces creeping down, so you don't get the impression of what the lightning shape is. And then if you use a longer exposure, you then get to see the whole shape of the lightning. Now, in the case of something that is not producing a point A to point B discharge channel, where there is actually something that's leaving a luminous trail, or it actually has physical size, then there's additional problems. And these problems are to do with the type of imaging technology that is most prevalent these days. And that is, rather in the old CCD days, they used to take an entire frame in one go. So every picture element on the CCD, it would take a sample for the duration of the shutter being open of the entire frame, and then it would store that, and then it would take another sample of the entire frame. What you have now is these things called rolling shutter, where it rolls down the image. And the first time in this science where it was very, very prevalent was the explosive events that caused the shutdown of the three-phase power supply when we were with Suhas Ralkar in his lab in Mumbai. And I was using a range of cameras. There was a GoPro, there was a Canon 7D, and there was a spherical camera. And all three of these cameras exhibited this artifact because of this rolling shutter. Now, sometimes they could capture a whole frame when the entire room was illuminated, but in every case, there was some frames where one or other of these explosive events caused the rolling shutter to record illumination on a part of the frame and no illumination whatsoever on the other part of the frame. And bear that in mind when you look at what I'm going to show you tonight. Now, what I am going to show you tonight is something which is going to have some Russian subtitles. So I'm trying something new here, and so hopefully above my left shoulder here, you will see some Russian subtitles. There we go, and they're going away in the background. I actually wanted Italian or French here, or Italian and French, but that's going to take a lot more work to achieve. But anyway, there's Russian subtitles there for those Russian speakers that are interested in ball lightning, and I know there are many. So you missed the first few seconds. Jason, don't worry. Okay. Yeah, and I want to thank Bido for his support, because what I've been able to do is to get some devices that are really rather affordable. In fact, they're scarily affordable. The kind of replacement device I would have paid for and did pay for in the past to achieve what I'm achieving right now, to show you this camera here, and basically bring this camera back to life, is a device that is able to capture the HDMI output and convert it into a USB 3 source that can go into your switching software. In this case, I'm using Open Broadcaster software. And so what this is enabling me to do, hopefully, when we run the Supernova and other experiments, is to be able to pull in, using cheap, affordable cameras, some of the best footage you can possibly imagine. And this is where we're going to target to at the end of this presentation, because this is the kind of normal GoPro, not GoPro. This is the Logitech 910C, and what you can't see on this Logitech 910C are some hot pixels that are very, very obvious, and they have been when you do a black frame. And these appeared when I was exposing this camera to the Echo Fuel in 2017. Now, on the Canon 7D, for which you've seen many, many videos produced by it, there was a period of time where I was looking at lion samples, and I'd already used this camera for taking pictures of the glow sticks experiments and for Suhas Ralkar, where these explosive events, and in the case of a range of different things. And I've collected quite a few extremely hot pixels on that particular camera. So I'm going to switch back to the other camera here. So you can see the real difference. So it's not only in the saturation. Here, and what a lot of cameras tend to do is they can tend to smooth out features. And in fact, they're doing that in software and AI, principally driven by the desire to look like you don't actually look. And that is not useful for science. You want the reality and this is much closer to reality, the reality of the imagery to capture the truth in the data. And so there's a lot of topics that we're going to be discussing here. Okay, so I'm going to... hi, Peter. Okay, so we've got a fair quotient of people in the room, and hopefully for the Russian speakers, this will make sense. Okay, so I'm going to switch to the presentation slide here. And what happened is, over the last several months, the Vega experimenters, firstly that's Henk, who started this on his own initiative, and then Dave, they're both up to speed. And the good news is that one system is for 230, 240 volts at 50 hertz, and the other is at 120 volts, 60 hertz. And now this might be important when you look at the imagery I am going to show you. It may play a role in what you are seeing. Certainly, certain types of cameras, like CCDs, are more susceptible to interference with the lights, for instance, fluorescent lights or other type of lighting that might be pulsed in your environment than a rolling shutter is. So there are some advantages, but not when you come to science. You want the image to be the image that frozen in time and it to be accurate. And ideally, you don't want to be having gaps in time. And you will see in this presentation that there are gaps in time in the image, which is very similar to the gaps in time that were observed when I was sharing the images from the Suhas Rao car explosions. I think I called that video "Brilliant Light Shower" because there was a kind of shower light around it, and yeah. Anyway, so what we're looking at is in I think the 1910s, Irving Langmuir, who was the inventor effectively of the tungsten light bulb, he found that he had an evacuated chamber, and he was testing the tungsten light bulb in there, and what he found is that it was producing a vast amount of gas, and he didn't know where this was coming from. I think it's something like 7,000 times the volume of the filament. Now, I would argue that this is water that goes through the borosilicate glass, or is still residual water in the volume of the evacuated chamber. And this goes to the hot tungsten wire. It is disassociated. You get atomic hydrogen. The atomic hydrogen causes the disintegration of, well, it can produce exotic vacuum objects, as we know, and whatever causes disintegration of the tungsten, which is something that has been observed first, I believe, by him in these experiments in 1910s, and by many authors, for instance, by Matsumoto, David Hudson, by Mizuno, by most recently the Sapphire team, and so forth. So these are times when we've observed it in the Vagar experiments. And so that is the reason for choosing the tungsten in there, because it has this long history. And in fact, I believe it was Irving Langmuir that actually, he was meant to be doing a teaching job, and he went to his sponsor, I think it was General Electric. I think that his work made General Electric. But he went to his sponsors and asked, there's this anomalous production of gas going on. I'd like to be focusing on that rather than teaching. And I think he was actually sponsored for 5 years to do that. So this is not new science. However, what you are seeing on this screen, if I can show you here, is a anode which was made by Henk. And it's got a lot of the learning that we've had during these Vagar experiments. And you've got the sphere. The sphere is a minimum energy surface. It is the smallest surface that can hold the maximum volume, and the only other one is the torus, and that is, I believe, why exotic vacuum objects form these basic structures that then can aggregate into much larger complex forms. And then he's drilled some holes in here. And I'll come on to the specific reason why he believes that holes are a good thing to put in there. But what we do know is that the balls of lightning, these balls of fire, these technologically produced ball lightning, they like to congregate on edges. And why is that? Well, they're a kind of a focal point, aren't they? And what he's done is he's cut 2 holes through this anode, and he's passed through one side, one axis, he's put some nickel foil, and then through the other axis he has put some tungsten rods. Now we know nickel can dissociate hydrogen. He has hydrogen in his cells, typically with some argon, but low pressure after it's been evacuated, and some residual air. What will residual air hold? It will hold some small quantity of water. Refer back to what I said about Irving Langmuir. And so now what we've also established is that if you can see here on the actual electrode whilst it's in the reactor, we have one large ball of light here, and we have 2 small 50% sort of, and we've discussed these before, self-organized plasma structures here, and with this kind of a fall-off area. Now, the thing that is we've demonstrated, I think, conclusively before we knew it was already part of a discussion, is that these things can wet into each other. They have a surface tension. They would like to reorganize themselves around the electrode. They are attracted and they are repelled, and they do focus on surface features. But once they've located themselves in a place, there is a 2011-2012 book we've shared in the past where it seems that they always want to go back to that place. So there's potentially a shadow left in the material that guides the structure to form in that place. Now, is it because there is something that's stuck in the metal that encourages the formation of the ball lightning in that place again? Maybe. Now, the other thing is when they get energized to such a level, they kind of like grow and grow, and then they almost have quantization levels, and then they snap and they'll join and they'll wet into each other. The interesting thing with this ball here, this very large ball that you see, is that it has its base, effectively, if you look down the bottom right of where I'm moving my mouse, it has its base curvature stuck in the rim of the hole that goes through. And this is not unsurprising to us, but it would appear, if you look at its dimension, that either this side or either side, that the outer edge, that is the top edge up here, is at the far end of the tungsten welding rods. And this is not, we've seen evidence of this before. Firstly, if you look at other Vega experiments and images that have been shared, if you have a tungsten welding rod, little balls of fire form on the end. So you've got a little ball of fire here, and then you've got balls of fire around the rim of the large hole. It would appear that when we looked at where you've got 2 resonant structures, and the one that's not on the open end of a coil, the one that's opposite, it will cut on either side of what I believe are coherent matter membrane that's right between the sort of nothingness in the middle, or very little going on, and all the action on the outside. And why do I say that? Well, there's evidence in the historical record. If you go and look at some of the studies of Dr. George Eagley, he found that sand didn't sinter and came out of a ball lightning having been carried, i.e. that its mass and inertia had been negated so that it didn't fall under gravity. But when it disheveled, it dumped the sand. The sand had not been sintered, and that's not pure quartz, but you would imagine that there would be some sintering going on if it's able to cut tungsten. You would imagine that potentially one of these kind of structures might sinter sand if it was really hot in the center. But the more interesting one is another example where water came out of the ball lightning. This implies that it was even below 100 degrees C inside the ball lightning. On the flip side of that, there are examples where a ball lightning has gone through a wall. It has vaporized metal wiring in a wall. It's gone through a concrete floor to find rebar that's in the grounded and that's in the concrete. So it's on its boundary, it's able to cut through glass, it's able to cut through rock, it's able to explode. But more interestingly, and specific to the water example, is you have a ball lightning and it's able to go into like a barrel of water and boil the water. It's able to boil the water, but ball lightning, obviously they're different events, so there might be some parameter that's different between the two. But the ball lightning can carry water and not boil it. But when it goes into water, you can imagine that this layer on the outside is interacting with the water and boiling it. Now, here is an interesting thing I'm going to drop for you now. It's a little key to the kingdom. If you are creating micro ball lightning in cavitation systems, in Brown's gas generators, for instance, or in Ohmasa gas generators, as it would appear our studies have shown, then you could have a scenario where this self-organized coherent matter plasma structure is able to disassociate water with almost no energy input. Think about that for a minute. Why? Because this coherent matter boundary has this massive ability to interact with electrons in a non-thermal way. So water would then fall apart. So you have these car technologies where someone had a kind of device that maybe had very close electrodes. And you would imagine that if this was vibrating and causing cavitation, that if there was micro ball lightning being formed in there, it could do a micro version of what I'm saying is happening when that large ball lightning goes into a vat of water. It's not just boiling it potentially, it's actually disassociating the atoms in the water molecule. This would explain many of the over-unity claims for water-based technologies where you have vibration or you have electrodes in the water. Okay, so let's get on with what we're seeing here. So what I'm arguing is that this ball lightning is between the rim here and the outer edge of the tungsten. So that is kind of it forming. And you have electrons congregating around the anode, but you also have this focal point on the end, and somehow it's made this sphere. Okay, so let's see if we can play this. Now, what I'm going to do is I'm going to start by playing the three videos of interest all the way through. And part of the reason for that is that at least in one case or two cases, the encoding method does not easily allow you to step to and fro because it's based on looking forward and back in frames in terms of the encoding. But I'm going to do this now. We'll see where this takes us. Okay. So I'm just going to check you can hear the audio. You should be able to hear the audio. I should be able to monitor it over here. I'm going to get rid of my ugly mug out of the way. You can just see the transcript up there for the Russian speakers. Okay. So let's see if we can play this from the beginning. Okay, I'll play that again. And a third time. Okay, so this is the first video that showed this potential effect that we will be discussing today. And it is a group of effects that I would like you to think about. And I will present some hypotheses of what might be going on, and you can take away and think about it. I'd like to know your opinion. But essentially, the feature that's difficult for me analysing this work is the fact that the camera is handheld. This does two things. You have translational and you have focus issues. So as you're moving the camera around in your hand, I'm going to go back to my ugly mugshot. As you're moving the camera around in your hand, there's translational movement, and also you might be going in and out, and that changes the focal point. And that makes it difficult to stabilize. Now, I have stabilized it, and some of the images you've seen are segments which were able to be stabilized well. But I've been talking to the researchers for some time in one case, but it's very important to try and get a stable camera over the source of the data, because that makes post-analysis far easier. Anyway, that doesn't matter in this case, because there are some features in there that I would like to draw your attention to. So this was the first time they were observed. I'm going to step through this now, and I can actually do that on this video. So let's have a look. So I'm gonna kill my mugshot here. There we go. Okay, so you can see. Okay, so there you go. You see those two shots. Okay. Now, what do you notice in that two shots? You've got one ending here, and then it restarts here. And what that is, you're seeing there, is that from here to here is one exposure time during that frame. Okay? Then it records the frame and it goes to sleep for a moment in time, and then it starts up again when the particle is over here. This isn't a particle blinking off. You might think it's a particle blinking off, but it's not a particle blinking off. It is the dead time between the samples for each of those frames. In both cases, Gordon, the technology is AC. Okay, and that will be important also. Okay, so we've got a lot of frames to go through. So, okay, so what you will notice here, so here's a selection of frames, and I actually grouped a number of these together, is that around the ball of fire, this macro ball lightning, it would appear that all of the particles are coming out essentially, mostly, perpendicular to the tangent of the sphere. That is less so as it approaches these structures here, these ball lightning here. But certainly from the sort of the 90-degree around here, you're kind of seeing it almost come out perpendicular, and most of them will do that. But the interesting thing is here, the field, as it would appear, we have shown in previous experiments where a ball lightning attached to one piece of tungsten in a VEGA experiment, when the tungsten fell away because the other ball lightning cut it on this coherent matter area, it fell down and the ball lightning oriented it to the one that was remaining on the open end of the cut wire. And this shows potentially that they have a highly organized magnetic structure. And this is not something that is new. People have said this about ball lightning, and it's part about why they orient. But it's different. I haven't seen so much discussion of it within this context. So what I'm saying here is that the magnetic fields of these two self-organized structures on this part of the material, the anode rather, is causing this to deflect. Okay, now I'm going to step forward one frame, see what happens. It deflects in a different direction. So it's coming there and then it changes. Again, you can see the gap between the sampling frames here, and then it starts again here. This is why imaging is important, and knowing how the image was produced is important to understand what's going on. There's a subsequent frame, you can see this one's deflected, and then it comes over here. So there's something down here that's attracting it. But when it's going past these two balls, there is some deflection occurring. So this, I would believe, supports the hypothesis that these self-organized clusters, they are exhibit a strong magnetic field. Of course, you would suggest that then this must be charged in some way. Okay, look at this one. Look at how much that's deflecting. So this one's coming out at this point, and this one's coming out a little bit further up. Now, it would appear then that for some reason, this particular state, these are either slightly more energized or whatever, but it's trying to come out at a tangent from the, remember the inner layer is a little bit inside this bright area here. It's coming out, it's bending a lot. It's bending, and then it has a trajectory that then goes down here. Now, why is it going down? That is, I believe, going down. I believe that this might be positively charged, okay? And why is it going away from this? It's been attracted to it, so it suggests that at this point it might be negatively charged because this is an anode, okay? But when it comes down here, is it going down towards the cathode? I don't know. Like I say, I'll share these videos, and I think there's a lot to be learned from them. Okay, so we've got one, it's not just coming out of this side, we've got them coming out of here. So I'm going to step through faster and find some frames that I want to discuss. And now look at this one. It actually comes out here, and it goes, and it appears to go and merge with maybe a ball that's out of shot on the other side here. Now, at this point, watch this ball here. Something comes out of this ball, and it goes around here. So it's not just the big one that's producing these. So this one looks like it's being attracted to it, and then it's kind of almost being deflected. Could it be that one is an innie and one is an outie on this? Like this is pulling in, this one here, and this one's pushing out. There's a magnetic loop, half loop, a soliton between these two balls. Could that explain it? In this one, look, it goes out here and it goes all the way around. It almost follows the curve of the anode. Okay, I'm trying to get to the first of a different kind of. There. Okay, so I don't know if you can see it. It is subtle, but look at this plane here. There's something that emerges here. So it came out from here, and it's here, and it's travelled a large distance between the frame samples, and then look, it's a squiggle. It's a squiggle. What is going on with that? Why have we got a squiggle there? Now, I'm thinking ion acoustic waves, undamped AC, or is it something more exotic? Well, we'll go on about it. But we have a squiggle. Now, is this a spiral, or is this a sideways deflection? I don't know, but it comes out of the ball, and it comes over to here, and it's squiggling, and you can see the depth of it over here. That's not the only one. There are others. But this was the first time I observed it. Now you'll notice, as we get up to the sort of this beam, which might be something in the background, but it looks like it's a bit of a beam coming out of the top here. The curves go from kind of like being perpendicular and coming out that way to actually following this central line on the axis of the self-organized ball lightning structure. See, there's one coming straight out the other side, and we can see a little bit of a squiggle going on. And look, we have a large squiggle going on here, a large squiggle. Now, the interesting thing is here, in this one, I'm stepping forward now. Look at this one. It's coming in here, and it's coming in here. This one would look like it's not coming out at a tangent to the curvature of the ball lightning. The one next to it is. But the reason this is not coming out at a tangent is that this is coming into the ball lightning. Look, I'm back. I'm moving forward. I'm moving forward. It's coming into shot here. It's now moved over to here. You see, it's actually coming in. So that's actually one entering the ball lightning. Again, this one here, look, it comes out of the ball lightning and joins this structure over here. So this is almost like two suns sharing a plasma loop, a magnetic flux loop. See, it gets, as the closer it gets to the center line, the further it goes up. So when you first look at this, look, this one's quite random. It comes out, it goes out, and then it comes back in. And then we have this little tracer coming over here. Is it connected? I don't know. Like I say, I want your opinion on these moving forward. Look, there's another squiggle. Big squiggle. Now note, some of these are just straight, or straight curves, if you know what I mean. Now here is a very large squiggle, and the interesting thing is it doesn't appear to come from this ball at all. It's much less strong curvature on it in its undulation. Okay, I'm stepping forward. See, this one's a coming in, so it's not coming perpendicular from the ball. Some of those can fool you. I'm going to, oh, there's another one where we've got a nice curvature coming round the plasma of these two self-organized structures, and then it bends away. Again, another one. Out, curves around, and then comes over here. There's this odd one that just pops out of the hole here and goes on its own merry way. Now, you may disagree with me, but I'm saying that the tungsten is, if we go back to the image, if we can go back to the image, this image here, I need to kill this a little bit and move it up here. I'm saying that the ball lightning extents is from the rim to the edge of the tungsten that's sitting out there. Now, why is that important? Well, it would have been useful if I'd taken some of the sparklers out of my cellar and done a video. But it would appear that it's coming from the center of the axis if they're all coming out perpendicular. Like there's a sparkler in the middle and it's sparkling. I'm saying it's not. I'm saying that these are emitted by subquanta structures that this overall ball is made from. It's actually a ball of other structures, and they kind of emit like on the radius of a clock. It's almost like not quite 12 points, but in kind of self-organized way. There seems to be a majority of them that come out of a fairly close zone around a ring, if you know what I mean. And it becomes more apparent when you look at the composite shots that I've done and shared, and will do in the coming days in expanding the newsletter article on this. So let me go forward again in this. So here we get a lot of movement. More coming out the other side, you see. Same pattern, you see. This is coming out perpendicular to the curvature. Perpendicular to the curvature. Perpendicular to the curvature, and then it bends away. Perpendicular to the curvature. Perpendicular to the curvature, but it's attracted by these self-organized structures. This one's a little bit squiggly. Not immediately obvious. There's a big squiggle. Look at this one. Oh, now this again is not coming out. I'm going forward and back. So that's before, frame 2, frame 3. Look at that squiggle. Now, is that a spiral? Is that a spiral? Or is that just a to and from displacement? I don't know. Is it like just a lateral sideways movement? Is it an ion acoustic wave? Okay, we're nearly at the end of looking at this in detail. So I'm now going to go to the second of the videos, and this came from Dave. And these first videos were done with 240 volts, 50 hertz and AC, and these are done with 210 volts and 120 volts and 60 AC. Okay, so it looks like its own plasma nebula here. Now, typically, when you get these things going, you strike an arc. And Dave's been very inventive. Like I say, we chose tungsten and nickel because of their known ability to play a role in Lennard experiments. And in the case of nickel, to dissociate hydrogen. Obviously, tungsten can get very hot, so that can dissociate hydrogen. And here we have, as I understand it, a nickel foil. And you have in the background there, you have a copper cylinder with a hole in it. In the hole is some melted indium. Reason being is that the majority of indium is an isotope that is a beta emitter. And in the center of that indium is a tungsten electrode. Now, of course, if you have tungsten and it's white hot, you would imagine the indium, which is like one of the lowest melting point elements there is, that isn't an alkaline metal and is actually a solid at room temperature. You would imagine that to instantaneously become a liquid. But anyway, that being aside, I rather like this experiment. But initially you strike an arc to get the plasma to a certain state. So I'll just play this playthrough. Very good, Gordon Doherty. Yes. Yes, I think you're right. I think they are moving along field lines. Yes, I think they are. Okay. So let's have a look at this one in a little bit more detail. This is again an anode. It's got some self-organized plasma structures along the rim of the tighter, further part of the spiral, and a large self-organized ball at the open end. Now, this video, you can see the encoding method is not so good for stepping through. Okay, but you can see here the similar sort of thing, that they are coming out perpendicular to the ball. I would argue that the metal of this nickel goes all the way to the coherent matter boundary layer at this point. But you can see at this point they're coming straight out, and they're coming out to the side over here, even though the metal is going all the way through. So I believe they are being emitted actually by the boundary and not the piece of metal in the center here. Okay, and you can see that they're coming out, and also you can see the squiggles. Now the interesting thing is here, when I was thinking, are these ion acoustic waves? Are these to do with the AC frequency that's being used? Is there something else that's going on? Is it some kind of like cyclotron thing going with very large charged particles or very massive particles that are small, or whatever? What is going on? Because some of these are straight simultaneously in the frame as ones that are squiggled. What is going on? Seriously. There's a lot of straight ones there, but there are some squiggly ones. So the encoding doesn't do well going forward and back so much. Now look at these. There's several types. There's these large kind of tracer ones, and they kind of imply that they're going back this way. They're coming in. But again, it could be because of the way that the video is being sampled. So I have to give Henk full credit for being first to make his data publicly available, and Dave, as you'll see, to taking it to the extreme in his experiments. And this is not something to be messing around with at home. However, we've had a discussion within the MFMP and with Dave and Henk. And for those people who are willing to say, like on video, yeah, and write it like, we know we're taking a risk, we know that this is high voltage, we know that this can kill me, we do not hold anyone liable, blah blah blah, and taking their own risk. For those people that at this stage, we will try and make available the plans depending on which side of the pond you are. So that you can maybe explore doing these experiments. But we've already been approached by a couple of people, and we would like to be able to try and support those people, both in terms of safety and in terms of if they have a particular piece of equipment that they need, maybe support them there. I know I've reached out to Numa Tech Prototypes and started a bit of a dialogue there. He said he needed something, so I think it's the overall thing here is that this technology or families are related to it has killed people. Whilst I admire the bravado of doing this, you know, if you have a young family or you want to have children,
do bear that in mind, that this is very, very seriously, potentially extremely dangerous work. Okay. And when you see these things flying around and having this spiral nature, so look at this one up here. This looks less like a translation. I don't know if you can see it on your particular shots. And you will notice that some of these beeps from the Geiger counter are correlated with flashes. Some aren't. So you can see that the ball can stay there for a fair period of time and not actually throw out sparks or whatever they are. And then sometimes it's throwing them out. So there's a lovely set of squiggles here. And you can see this, the squiggle appears here. And then on the next frame, it's over here. But the encoding's not so good for showing that. There seems to be a matched pair that were launched exactly the same time in this case. And this, because they're so correlated in the wave function, this would imply to me that they're, you know, either they're entangled, or that there is some ion acoustic wave going on in there, or it's some sort of magnetic fluctuation due to the AC. Very, very clear here. Look at this. Look at that one. It has a very long wave, when over here you have one with a very short wave. Now, and then you have one with a medium wave here. So it looks like, you know, this has got a much higher velocity. So maybe there's a common fluctuation that's going on, and because it's traveling at a slower speed, it's expressing a less significant sideways motion. But look, it's got all the way over there, and then it comes over here, and it has a very bizarre different movement. So in the next video, I'll be able to show you where you have ones that are going in dead straight lines, and there are ones that are wiggling, and there are ones that are curved, all in the same frame. So if you think it's ion acoustic waves, or you think it's magnetic field variations en masse in the entire environment, it doesn't really fit the data. What it might fit the data is a certain type of wave that is corresponding to a magnetic flux line, a magnetic field line. And I will talk about that in a second. Okay, so the last of these videos is kind of like turned on its head. And in this case, we used aluminium, and aluminium has been an element that's been shown to be affected by ball lightning, and this was observed by someone who gave their account to Dr. George Eagley, which I've recounted in the past, where a ball lightning came along the side of the train, it touched the aluminium frame of the window, and for about 20 minutes the person was able to manipulate the aluminium with his fingers cold. This anecdote is very similar to when Alec Pizarro was able to pick up a Hutchison sample and leave his fingerprint in as it smeared a certain amount of the outer layer of this sample that had just been exposed to the Hutchison effect. And this is very similar to Ralph Ring when he was working with T.L. Carr, and they used whatever it was that's supposed to create some sort of anti-gravity effect, and the aluminium became like jello, and he said he was able to put his hand into the aluminium cold, and it didn't like wet to his hand. It was almost like a silly putty, and he was able to pull his hand out. aluminium was the most effective material in the Hutchison effect. And so, and if you look at the Salvatore Pie, I think they have aluminium as some material that they're using in those patterns. So aluminium was chosen for these many reasons over a long period of time that it seems to be effective. And I believe it's because it is a monoisotope. Aluminium 27. It has an NMR moment. The nucleus has an NMR moment. It is highly conductive and it has a low melting point. That is, the lattice bonds in the metal are holding together in a less strong way than, for instance, tungsten. They're less tightly aligned with each other. They want to be with each other less. So when you've got something that can come in and it is able to disrupt the nature of an electron, that aluminium wants to fall apart. So it has more conductivity, so there's more availability to the EVO, the exotic vacuum object, of the electrons in aluminium, and the way that the metal is holding together is less strong. So in the case of high conductivity, low melting point metals, they will go jello-like and deform well below their melting point. In the case of things like tungsten or iron, where you have either a high melting point or you have less desire to give up the electrons or whatever, you get to a point where they just fracture. They get to the limit of the exotic vacuum object's strength, and then they can just repel each other and so on. You see this in the Hutchison effect, and so it richly shreds the metal rather than turns it to a wet noodle. Okay, so the last video here is different in that what you have is you have the anode is here, and it's a different shape to the other anodes we're seeing. It's more the sort of cylinder shape with the edge on it. And this is the block of aluminium. Now, in the background, you will see this shadow here, and this is where a quartz crystal was, and where over here there were pieces of fluorite. The reason are, in the case of quartz, it is a piezoelectric material, and I am going to propose, and have done in the past, that it can be used as a passive detector for strange radiation. In the case of the fluorite, it contains fluorine, which I believe, again, a monoisotope, easy to cohere if you can get it into the EVO, and it has an NMR moment which is quite high, and I believe that it can provide specifically good fuel for the LENR process. They're not in this shot because they vibrated off extremely quickly, which does tell you that there are strong vibrations within this reactor. And so bear that in mind when we're talking about this. Okay. Okay, I'm going to play that once more through from the moment it gets. So there are two zones here. There's one in the sort of this area that gets affected, and there is another one down in this area that gets affected. And this is where most of the action occurs in this experiment. And in a very short period of time, it would appear that a fair chunk of the aluminium basically isn't where it used to be. Whether it's turned to a gas or thrown everywhere, who knows? The purple's probably coming from the argon, but you know, obviously you've got different spectral lines in there, and this will become important. Okay, that is pretty crazy, wouldn't you agree? What I'm going to do now is I'm going to go into Premiere. And the reason I'm going to go into Premiere is because you'll be able to see the frame numbers as I step forward and back, so that when you review the video, you'll be able to have a closer look at what's going on. Right, so let me just go here. Hopefully, I can get rid of this up here. And we've got Premiere in the background. And we'll just start over here. Okay, so even at the first flash, there is a massive production of these squiggles. You see that? And they're really rather intense. Now, I don't know whether this squiggle and this squiggle are artifacts caused by the lens components in the camera that was used to take this. Is this squiggle the same as this squiggle? I don't know. This certainly looks like it's a different squiggle, and it's at a different frequency from this squiggle. This one looks like it's going at a faster velocity, so it looks like it's going at a different frequency, but I think most of them are going at the same frequency. Yes, basically you have ions of argon in here, and they get excited, and when the excited electron drops down, it produces the spectral line. In this case, it produces a lot of purple. Very strong squiggle here. So I don't know if you've noticed, but down in the bottom left, you can see the frame number 1528, and then if I step forward, you can see it changing. So you can understand whether I'm going forward or backwards when you review this video. So here's one where it effectively looks like it's straight, but it is moving at very high velocity. Crazy. Okay, so we've got one that comes round here and goes round in a circle. Then we've got these ones that kind of go out straight and then bend over to the side. Could that be because there's no circular motion at this point in the plasma? Maybe it's circling around. We have shown that these plasma structures, they have a spinning motion in some, at least at some point. But then, so maybe that's on the outside, but on the inner part, there's actually no spinning. I mean, it's going in this direction here, this direction here, this direction here, this direction, but this is the opposite direction. And then the very next frame is a load of squiggles. It's like one frame apart. This is 1/30th of a second. Okay, so this is just one event. Is this a boson-over? This area down here, it seems to be a little bit more excited than the other areas. And then you just have this huge flash, and then the next frame you have these squiggles literally everywhere, going in all kinds of directions. And you can see, maybe you can trace them. So is this one there going to there, here to there? So in this case, the frame sampling stops at this point, and then the next frame is started here. This is why you need a different camera technology to be able to fully understand what's going on. For instance, this one here is further in the background, and then it comes over here. You're missing the motion in this area. Again, it's here, this one's here, and then it's over here. So you've got one here, this one here, it stops there, and then it restarts there. It stops there, and it restarts over here. And then and this is interesting, it goes through here, and then look at this one. It's the same one we've been following, and then what happens is, it just drops down. It just moves slightly over here. and then it disappears. Crazy. One flash. Immediately after the flash, you have a whole range of these being produced. Another flash, loads of them produced. Another flash, loads of them produced. And you can see that the flash was here, and you've got one over here, there's some shadows of ones here, and then those over there. Another huge flash. And then they're all over the place. I mean, this one appeared here, and then goes and appears to rotate. I have to say, it's an absolute honor to be able to share this with you. Absolute honor. Most people keep things to themselves, and it's just really nice that we have this working relationship. And I'm having the pleasure of being able to show you this. Look, so this one here, bursting out the side here, comes over here. Now this is very different from many of the other ones. And also, where's all the squiggles gone? It's literally a few. Look, there's a big squiggle there. There's a big squiggle there. There's one here which is a different orientation. The next frame is a big explosion. And it continues for 2, 3, 4 frames. There's this big orange glow here. And then it dies down and you get this thing coming out. There's no squiggles anywhere. All the squiggles have gone. And you got this thing coming out here. Very, very large structure coming over here. And is it the thing that causes this orange glow? I don't know. So these definitely look like they're aligned to something, because the hooks are pointing here, and then you've got a ring of hooks here, and then you've got a different ring round here, and then they fly out. What's that? There's another one of these large events here. Like straight after that, look. Big event, and then you see this structure, and it's coming up here. What is that? I'm not sure I want my head on the receiving end of whatever that is. Another one here. And then this one, look, it's like there's an event here and you just get this spray out. It's immense. And it goes over here. Many, many particles thrown out in one go. And we're back to having some squiggles. Squiggles. Where did they all go for so long? Look, squiggles. We're back to squiggles. Haven't seen squiggles for a while. Same system. And okay, so look at this squiggle down here. Okay, in this area, it's born. You can just about see it. Okay. Now, it comes up here, and then it changes its orientation, and it seems to be attracted. Now it looks like it's coming up still. Now notice, this is the end of the sampling point. This is the new part of the sampling point. We've lost a piece of data between here and here. It comes to here, and then it goes round there. What? It comes up, it rotates, it seems to go straight up, and then it rotates over here. What is going on? And then we're massive squiggles here, massive squiggles. And then it's like, that's the dying explosion of this one, with this huge trail coming over here. And then we've got some shadow of squiggles here, this like shepherd's crook over here. And then we're back over to this new area here, which becomes the new active zone. And interestingly, we'll be back onto squiggles very shortly. Look. And some of these squiggles seem to come out and then come back down again. Look at that. radially around this event, there's very many. Okay, that's my hour slot, so I've got 15 minutes. I'm going to go over because I want to show you some of the hypothesis. So it looks like there are squiggles, but we've got straight ones here and the kind of straight ones over here, but it might just be the orientation. This one looks like it's straight. We've got squiggles. We've got one that's a curve to here. These are one frame apart. Okay, I like this one. Look at this area here where I've got my mouse. Suddenly something appears. And it seems to bounce. It's like it like explodes out of itself. It's like it doesn't change its base position between these two frames. But it's here. And then it seems to jump up here. It looks like it's the same thing. We've lost a bit of data between this point and this point. But it's kind of emerges, springs up, and then it's like something that's unwound itself. This one comes out. It's not got a squiggle. It's kind of straight here and curved, and then it comes into the ball as the explosion is collapsing. It's moving in. This one on the outside is straight, and then as this one moves in, and you'll see that this one moves in. You see that one is on the outside, this one's on the inside, that one's in the inside, that's on the outside. Now watch what happens. They get shot up here. You've got one here, one here. Then what happens there? I don't know. It's like something comes back in. There's some sort of conflagration of a number of these things. They all merge at this point in space. And then they fly off together. It's absolutely madness. And then it dies back. How are we doing? We're about a third way through this. Half the way through this. Again, we've got this star event here. Look. Okay. So, look, there's nothing here. Nothing here. Then suddenly you have an explosive event. And this almost looks like the stars we saw on the fuel of Suhas Ralkar, and it also looks like the stars that Matsumoto observed. You got some event here. You got a bang, 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 something that curves round and bang, and then watch this straight bit down here. It then becomes a squiggle. It's like shifted. This end has come here. This end has come here, or is it this curve? It might be this curve here. Right. So you've got straight one, straight one, straight one, straight one, straight one. Or slightly curved. But look at this. This is fundamentally different. It starts at the center point of the explosion event. And it starts curving here. We lose our sample point here. And I think that is the same thing that's over here. But then it's got this circling down here. Is it a spiral? Don't know. Certainly from these ones, it looks like it might be straight. Because you see a little bit here, a little bit here. But this for me is one of the most amazing ones. Because there's nothing on the frame before. You don't see anything coming from any direction. Then there's an explosive event at a point in space. Some are straight, and then there's the start of this curve. And then the curve comes over here, and it almost like it comes down and hits the cathode, which is the aluminium, and springs up here. I wouldn't be surprised if this isn't this. And this is why it's so important to have the missing data between here and here, to know which is born from what. This is like it's rotating in. It's kind of like not in a perfect squiggle, and then it comes in and squiggles. Anyway, you can have a lot of fun with this. Here is a more of a tracer one. This less, like no squiggles. Like you've got a dead straight one here, dead straight. This is like a tracer. It's like soft, and this one is a squiggle. So is this one. It's straight, it's curved here, and then it becomes a squiggle as it comes in. This is probably some of the most remarkable video I've seen. And, you know, it might be something completely ordinary, and we'll talk about that. But it's definitely lovely to see. Now, we'll talk about this particular event here in a little while. Now, this is quite interesting. You see the squiggle here? Very clear. And it comes around here. And then, is this it? Don't know. But definitely this is the same one here. We lose the information at this point. We regain the information here because of this type of image sensor. Boom. Boom. Look at this one. It's again this little spring over here. Is there a nucleation point over here? I don't know. Look, it's a little point. Then it goes boom. And then it kind of like unravels and it loses its waviness. This one is so intense. Now, I actually believe that this is giving some very good information as to what's going on. This is this kind of prominence that you've got here going into this streak. This one's sort of going up, round in a loop and up. What? This is one of these large ejections. A real kind of a solar flare type thing. And is that, because did we lose information here to here? Is this the cause of this? Again, is this one of these points up here? Look at it, look at it. There's a little thing here. Boom! Spring comes up. Boom! This one, it starts like this little curve here, and then it stretches out. You've got a loop here and round. This is not some simple sinusoidal effect here. This is far more interesting. And I believe that we can argue it's due to magnetic flux loops. Again, there's this little spot over here. Boom! What's that? And then it becomes this. Look, looks like it's coming out, and then it becomes the squiggle, and then it comes up here. So it isn't like the field is evenly distributed or whatever. This magnetic field line or this magnetic loop, is it a magnetic flux line that is disassociated from its originator? What? This is huge. Comes out, looks like it hits the cathode down here, produces this long straight line. That is absolutely massive. That's in 1/30th of a second. And then the whole thing shifts sideways. Goes from here to here, here to here. Starts off there, goes here to here. What? Okay. Something here produces this huge beam, and then it kind of like, does it go double back on itself? Don't know. This one comes out, springs up, out, and then is it coming back? No, no. There's another one born here, comes out. This is literally like a solar kind of like magnetic flux loop here. And you've got another one over here, and it comes out. And then it comes up. Okay, I think you get the idea, and you'll be able to play with these videos in your own time. And I'll be very interested to see what you've got to say about them. But we're going to talk about some different concepts here. Just see if there's a couple of lovely ones. Here, look, you got squiggles and you got incredibly straight ones. And look at this one, it's so straight, such a long track. This one's beautiful. Look, you get it up close and personal. It's down here and it comes up. Here, see it? See it? Absolutely beautiful. And then it actually goes through the anode. It goes through the anode. It's in front of the anode here. What is going on there? It's like a big comet, but it has this long structure. Frame 1. Frame 2. What? Again, you've got curved ones and a very long straight one. They might be charged. Some are charged, some are neutral, maybe. And it's the charged ones that are, you know, or magnetically charged or in a magnetic flux loop that exhibit these things. Look at this one. What's going on? You've got a little squiggle. It comes down here, touches the cathode, and then comes off at an immense speed. Absolutely crazy. It's bonkers. Again, another one here. Big flash, and then this comes out. Can't be a coincidence that these very highly energetic ones. Now, I don't know if you can see it, but it is there. It does look like there's some sort of spiraling nature going on there. Okay, we're nearly at the end of this, and then we'll look at what we might be looking at. Look at this. There's a big comet trail one here. And these were observed by the Sapphire Project, but long before that they were observed by Shoulders. And actually Shoulders has some very clear imagery of these things kinking and changing direction, as we've observed in these experiments. And also two that are spiraling around each other. And when you look at some of these images close in, it does appear like they're spiraling, but it still may be an artifact of the imaging technology, and we must be aware of that. So again, this one born here, it shifts over to the right, it then comes and becomes a spiral here, and then springs up. What's going on with this one? Again, when you get these big blue flashes, very, very different. Very different to these kind of things. You get this very big blue flash. Very, very highly energetic. And this really does look like, I don't know if you can see it, but this really does look like there's a spiral component on there. There's a spiral component on here. It's absolutely immense, this track. In fact, no, my mugshot's still not coming it up. What's going on here? Up, down, round, straight. And it starts off as a little knot loop here. And then it goes, what is going on? That's the frame before. That's the next frame. That's the frame before. One end has gone off to infinity, and this one end's just crept over to the side a little bit. Meanwhile, the whole thing occurs where you've got a nice sinusoidal one down here and a nice sinusoidal one down here. Another bluey tinged flash and this huge energetic particle coming off. Okay, so this one, it comes out, it kind of hits here, becomes a spring, and then bounces up. Another kinky one. Look at that kink. Comes around, it's curved, then it's got a kink, then it comes up here and it's straight. Okay. Major blowout at the end here. Boom! comes loads of squiggles. Okay, so look at this one. So this squiggle appears here. It moves over to the side and appears to shrink. Okay, this one here, again, moves to the side. So it's moving in this direction. So these two. Then what happens is it comes back in as this shrinks. It comes back in. Okay, and then it shoots up. Oh, no, sorry. It shoots up and then it comes back down, coils up into a tight spring on the cathode again, and then launches itself up again. It's like it's an entity in its own right. Now, string products were observed by Matsumoto. They were then observed in plasma flow discharges, where there's a water flow and they're doing high DIDT discharges onto a metal plate, by Bogdanovich at the Moscow Nuclear Research University. And they saw these glowing string-like objects. Now, are these things? Are they? Are they chain clusters? Here, this one comes out very energetic, curved, comes up there. Okay, so we're nearly done there. One very large one at the end there. Okay, right. Yeah, the flux loops are insane. So what I'm going to do now is I'm going to walk through a whole load of things. So firstly, are we seeing Birkeland currents? Are we seeing Birkeland currents? Now, this was produced by Birkeland, and it was auroral-like Birkeland currents. And I'm going to get rid of my mugshot here, so you can just see the Russian there. Okay. In fact, if I move this over here, get to see my ugly mug as well. Okay. So this is auroral-like Birkeland currents created by scientist Christian Birkeland in his Terralia, featuring magnetized anode globe in an evacuated chamber. So as far as I understand it, he's got two cathodes, top and bottom, very much like the Sapphire project, with an anode sphere. You can see this electrode support here, and it's magnetized. This is magnetized, and it wasn't until the patent of Sapphire was released that they revealed that their anode was magnetized. Now the thing is that these currents are coming from the polar regions. Our ball, these balls that I've been showing you, we haven't got a magnet in there. It would appear that they're creating their own magnetic field and the ejections are coming from it. So you would imagine that the sun is creating its own magnetic field and the ejections are coming from it. But there are submagnetic fields within it. And I believe that this is important in understanding what you've just been witnessing. Okay. So yes, I think probably conscious energies, there may be some double layer fields going on. There certainly seems to be some trapping in these layers of these structures, and as the explosion goes out and then collapses, the squiggles go out and then they move back in again. It's absolutely fascinating to watch. Okay, so this is a very good site called Plasma University. There's a lot of information on here. And what could we be referring to? Well, here is a list of plasma instabilities. It is not insignificant. There are a lot of them. You can go through them in your own time, but here's some: beam acoustic instability, bump in tails instability, Brevin instability, Cherenkov instability, Chute instability, coalescence instability, collapse instability, counter streaming instability, cyclotron instabilities, including alphen, cyclotron instability, electron cyclotron instability, electrostatic ion cyclotron instability, ion. There are a lot of different things that could be the explanation for this, but you need to bear in mind that some of these things are discussed on the scale of suns, and some of them are on the scale of black holes. These are not all things that are discussed in this kind of scale that we've got going on in this reactor. What are the things that could be applicable in this reactor? Well, there's a lot of questions that need to be answered there. I like some of these things here. Gyrotron instability, I like this helical instability, helix instability, what's that? And a helical kink instability. So I want to show you a couple of things here that may be the explanation of what we are observing. And I think there's a lot to be thought about here. So we have seen diachron instabilities. We have seen this in the Lion reactor, in the magnetohydrodynamic structures that formed in the reactor there. And I pointed this out when we did the first look at the this little sample here in what I call the Western Plateau over here. There were some structures where the plasmoid, the ball lightning, had come down and it had gone along the surface, and we know it spins these structures, and it had caused these little balls which had a little loop very similar to this diachron instability that you see here. So just put that in there. But this does create a wave when you've got shearing forces and so forth. So could this be some explanation for it? Well, there are also the double helix in outer space. Now, this is actually coming from a quasar, and I think this is a very famous quasar, and it's an ejection, and there's another view of it here, so you can see this helical ejection from the jet that's coming from the quasar. Now, is it self-organizing the plasma and causing a jet and causing these spirals going on? Let me see if I can bring up Photoshop here, because there's a lovely shot which has many of these features in it. Have I actually got that one there in Photoshop? Let me have a look. Photoshop. Yes, I got it here. Dum dum dum. Right, let me see if I can bring this up here. Is it going to let me come up here? Yes. Okay. So this is a frame from Dave's the second video that I showed you. And I think this is quite important because it does demonstrate that there's not a global effect going on here. We have a straight line up here, okay? We have an extremely straight line here. We have a curve with a bit of a kink, which seems to be going round in a radius. And it's this video where we had 3 frames and it's coming up and it's kind of looping round. So there is some sort of vortice around the whole structure. We have a kink over here. But this is what I really think is very interesting here, because this is clearly a spiral. It's like a flux loop that's come up and it's formed a kink. And this, I believe, is a kink instability. It's a magnetic flux loop that has formed. If you go down to here, you can see that these kind of have a spirally structure, and you'll see this on other frames. Maybe I've got one I can show you. Have I got one I can show you? Maybe. Anyway, so there are various frames. This, you cannot just make an assumption that there's one overall effect that's going on, because this is a single frame, and there's all kinds of, like I say, you've got the comet trail one here, you've got this curved in this kind of oscillation in this frequency, this oscillation in this frequency, this is straight but maybe with a twisty spiral on it, and this looks like a kink instability coming out of the overall plasmoid structure. Okay. Let's put that down there. There's our guiding light. There we go. Okay. So, and if we go here, what am I showing here? This is a presentation that is talking, a paper that is talking about these kind of things. So this is from Tiber Torok, Bernard Klein, Mitchell A. Berger at the University of Exeter, and Mark G. Linton. It's the evolution of writhe in kink, unstable flux ropes and erupting filaments. I believe this is kind of what we're seeing over here. So let me see if I've got the PDF somewhere. maybe I can get that up for you. Is it this one or this one? I think it might be this one. Yes, no, yes, yes. Okay. So, so that you can get this paper yourself, the DOI number is here. So you'll be able to, I'll get my ugly mug out of the way. There we go. Let's kill myself here. Right, so this is the DOI number, so you can go and look at this. Not cited by enough people, only 12, as far as I'm concerned. And we go down. So here we are looking at some features on the sun. So this is this kink instability here. And I wonder if we are not seeing something similar here. Is this a kink instability type structure that we are seeing here coming out? And they talk about the formation of these things and in the magnetic flux loops and various formations there. So what I'm saying is these experiments that can be done relatively affordably may possibly be showing features that are typically only mathematically modeled. I'll come back. So let's go back here. My next up is this. This is a paper by, again, Giovanni Lapenta and Marina Skender, and it's in the New Journal of Physics. And it is role of electric fields in the magneto-hydrodynamic evolution of the kink instability. Okay, and I have this, I think, here. Look at this. Look at this. This, according to them, is a mathematical representation of, maybe I can close that off. Can I close that off? No, there we go. A mathematical representation of what may be going on in, let's see if I can zoom out. The spiraling that you see on here is not very clear. I'm going to see if I can find one where you can see the spiraling in the structure much easier. Let me see if I can find that. Windows. We'll try this one. Okay, this is a group together. So I don't know whether it's clear to you, whether you can see this spiral. Now you can see that if it is like this, and what it's saying here. What it's saying here is that it says that the false color representation of net charge, gray lines represent magnetic field lines in the flux rope. Magnetic field lines are twisted and superimposed in the volume, rendering the net charge measured as that E. So is this positive charge and negative charge? So overall, there's in the whole flux rope, there's potentially no net charge, but there is charge separation. This is something that Ken Shoulders went on about all the time. Are we seeing a spiral here? Is that a spiral to you? Does it look like a spiral? Is it a spiral? Are there two different types of spiral there? Okay. Are we seeing what the theory is suggesting here may be going on? Okay, and is that something that leads to these kind of kink instabilities that we are seeing in that other image here coming out of this very large eruption here? And as I was going through the video, I pointed out these kind of structures where they kind of went up and they went round in a very tight loop and changed direction and so forth. These existed in what we saw. Okay, I'll take my mugshot out of the way so you can see the kind of spiral example at the top and the kink instability at the bottom. Okay. Okay, so let's go back to potential candidates. I'm missing something. No, I'm not. I'll come on to that later. That should be... well, I'll talk about it now. This is the difference between various shutter speeds. So if you have a long shutter time, you end up with the motion blur. If you have a very short shutter time, you end up with something frozen in time. What we ideally want is something where the global shutter is open for the entire length of that 30th of a second, let's say, if we're capturing at 30 frames a second. And then it reopens immediately in the beginning of the next 30th of a second, so that we can track the entire progress of whatever this entity is. And we can also see whether it's a discrete thing that moves from here to here as a block, or whether it's producing that mark as a trail over time. Okay, and so we can do that. I'll come back to that because I want to... This is the difference between a global shutter here and a rolling shutter, and this is why you get terrible distortion on rolling shutter. Anyway, I want to talk about the Alfvén wave. Why not? Because what this is let's read it. So, in plasma physics, an Alfvén wave, named after Hans Alfvén, is a type of magneto-hydrodynamic wave in which ions oscillate in response to a restoring force provided by an effective tension on the magnetic field lines. Where did I come from? We had balls which look like they've got their own magnetic ejections, and they are able to join from one plasma ball to another plasma ball, implying that you've got both within two little plasma balls and between a large one and a small one, and also affect them. In an Alfvén wave in plasma is a low frequency compared to the ion cyclotron frequency, traveling of oscillation in the ions and the magnetic field. The ion mass density provides the inertia, and the magnetic field line tension provides the restoring force. Okay, so if you have a very high charged particle and it's coming along a magnetic field line, it has its inertia in a direction, and then it's kind of bouncing around that magnetic field line. This is not producing a spiral so much as a side-to-side oscillation. The wave propagates in the direction of the magnetic field, although waves exist at oblique incidence and smoothly change into the magnetosonic wave when the propagation is perpendicular to the magnetic field. The motion of the ions and the perturbation of the magnetic field are in the same direction and transverse to the direction of the propagation. Is this what we are seeing? Is this what we are seeing? So there's calculations here. And I love this down here. This is kind of like your magnetic flux loop, and this is the Alfvén wave along that magnetic flux line. So is our magnetic flux... is it coming out a bit like this? We have an intense magnetic pulse coming out here. Are the magnetic flux line like this, and then the charged particle is traveling down that line? Sorry, get back to where I was. I need to go there. And what this is saying here, which I think is quite curious, is it says, magnetic waves called Alfvén S waves flow from the base of black hole jets. Or let's call them black donuts. I like to call them black donuts. So you can get these magnetic waves, Alfvén S waves, flowing from the base of black hole jets. Apparently, you can also see them in the sun. In this video here, this apparently is some Alfvén waves, but you can definitely see the magnetic flux loops on the going from the surface upwards. There are also these, which is effect of ion to electron mass ratio in the evolution of ion beam driven instability in a particle in cell simulation. So this is a simulation, but I kind of like this down here where you have a proton, an electron, and a oxygen ion here, and there is some oscillation in that. Whether that is similar, I don't know, but I'm suggesting that maybe, are we seeing Alfvén waves? Are we seeing this magnetic flux loop here, or the magnetic flux and a charged particle traveling along it? And are we seeing, in this case, a kink instability forming from this surface? This is something where, with really rather affordable equipment, are we able to replicate some things that are out there and that we can see in the cosmos? And how does this relate to EVOs? And what are these charged structures that have their own magnetic field and that are moving around and so forth? Is it just an ion? Well, I don't think so. I think this is a very large cluster of things that are moving. This is, would we see one ion? No. Would we see a whole mass of ions? Well, are they organized in some way? I would imagine they are. Okay, so now I want to talk about the problems that you have with video and how you get around them. Essentially, this is the global shutter problem, and this can cause wiggly lines. And the reason that this is a problem for us, if I shrink that back over there, is we are seeing wiggly lines. Let's go to this one, and we can see our wiggly line in this shot, which has a selection of different types of things. So we got one wiggly squiggle over there and one wiggly squiggle over there. I'm gonna bring up a different one here, because this is actually a composite of selection of shots. So you can see this curve and straight line here, but this is the same squiggle that comes from the base down here. Then it goes here, then it goes here, and then it goes here. And we are seeing the gap. I've combined these frames. We're seeing the gap between sampling. So the interesting thing is that as it comes up, it seems to be accelerating as it's being shoved round. So it comes up and then it goes round in a loop. And because there is a larger gap between the start and the end of the sample time. So the end of the sample time is here, the start is here. The end of the sample time is here, the start is here. It seems to be accelerating. It also seems to be losing brightness as it comes around here. But my point being is that because if we have a rolling shutter, we can't argue precisely that some of our squiggles aren't due to rolling shutter. We need a global shutter sensor. And unfortunately, these were essentially stopped being made in the early 2000s. To pretty much every camera you can possibly buy don't come with a global shutter sensor. The other thing is that you wouldn't want a global shutter sensor where the sampling is just on, say, 1/4 of the frame duration here. You want the sampling, as I said earlier, over the entire frame duration, so that there is no dead space between the end of the sampling time and the start of the sampling time. So what choices do we have for doing this? Here's some other. This is a different type of rolling shutter here. And these are the kind of squiffy effects that you can end up with rolling shutter. These are fan blades, or simulated fan blades. And this is what you see on a rolling shutter. It's obviously not the shape that it should be. And here's a point to note. This is on a Gen 1 CMOS. And this is another reason why we need global shutter. Why? Look at this. All these ones are on a Gen 1 CMOS with different times. And you can see that in this case, we basically see a nice smooth trail. But there are gaps. In this one, we actually see gaps. Now, could we misinterpret this here as the same thing that we're seeing here? Now, I do actually think that this is a flux loop spiral. This is a particle traveling along a flux loop spiral. But we couldn't necessarily argue it is, because with the CMOS that is likely to be being used in the sensor that took this, it might create these breakpoints because of the way that rolling shutter works. The Gen 2 is still producing these same kind of artifacts, and it's even worse with this Gen 2. So this causes a problem for us. It turns out that this claims the full. Basically, you need a CCD. A charge-coupled device will, for the entire frame, take a sample of everything that's in that frame. Okay, I talked about this at the beginning. Now, this is claimed to be a CCD, but you come down here and it's actually a 3 CMOS. Now, I like 3 CCD chips because one is for red, one is for green, one is for blue. You don't have a Bayer pattern. Basically, every pixel gets the right RGB value. So this has got 3 CMOS, but it's a rolling shutter. It has those problems that I've just shown to you. There is a camera out there called the Toshiba IK HD1, and this is a CCD. It does do 1080i, and it does certainly 1080i. I might even do 1080p, 1920 by 1080. It's 30 frames a second, and it has a YPBPR output. The problem is it is ridiculously expensive. It's ridiculously expensive. It is basically just the camera with a 3 CCD. So this is not good enough for our job. Why? Because as I told you in the beginning, I've had at least 2 devices, this Logitech that you're looking at me on now, and my Canon 7D, have hot pixels be produced on it because of exposure to linear experiments, in my view. It could just be the aging, but in my view, it was caused because of exposure to exotic vacuum objects. There's no reason why it shouldn't be, because they're things that would readily interact with these, being silicon and so forth. So we don't want to be spending $5,154 on something that's just going to be toasted the first time you expose it to a Vega reactor or something similar. And this doesn't even include any cabling, it doesn't include any means by which you can sample stuff, and it doesn't even include a lens. It's just the camera is $5,154. This is probably as much as both experimentalists have spent on safety and running their experiments to date. I don't know, but it's a lot of money. But we're going to end up with problem questions about what the squiggles are caused by, and we don't know what the path. We don't necessarily know that this one came from here. It's likely these are onion skinned together, but it's not certain that this one over here is because of this. We want to be certain that that is what's going on. Okay, so funnily enough, I owned this camera. I had to sell it in 2014 to pay 1 month's bills. But I actually owned this camera, and it was in the 2000s, and it was the first Sony high definition camera. In fact, it's 1440 by 1080 It does 50 in PAL and 60 interlace frames per second in normal kind of like frame size. It's not full 1920. However, it's 3 CCDs. So every single one of those pixels is the right color. It's not guessing. They're all the right color. And moreover, the outputs it has, it can give out YPB or YUV or whatever. It can give out that on a composite, not a composite, but a component output. And I use that very, very effectively in my work. And it's ironic that the only possible solution that I could come up with that's even slightly affordable used the camera, the last 3 CCD camera I owned. I had a TRV 900, my first 3 CCD camera. Then I had a PDX-10, and then I got the Sony. And this Sony was absolutely fantastic. Why is it fantastic? Because you can vary the shutter speed from 1/4 of a second all the way out to something like 1/10,000th of a second, I think. It's crazy. So, 1/4 of a second to 1/10,000th of a second. This means that you can capture a blurred image of the whole trace, or you can capture a very small segment of it. It's very flexible. Moreover, you can fix the focus distance. So you can, it's not trying to focus. A webcam and a camera on a phone is often trying to find the right place to focus. This, you can fix the focus. You can fix the aperture. It has an ND32 filter built in. If that's not enough, you can use something like this welding glass here and put that in front of the lens, and to bring down the light values so that you can adjust the other and fix the other shutter values, so that you can force it to take 1/30th of a second exposure of the whole CCD for each of the RGB values. Okay, and the interesting thing is, because everyone wants 4K and so on, and this is kind of like the first HD camera, you can actually pick them up very reasonably. You can pick them up for like £260, £300, not £5,154 without any means to capture it, any lens, any whatever. You can pick it up for like £300, £250. Okay, so that's not only what you can do. There's another camera which is exactly the same camera as the one I had, and it's called the Sony HVR Z1. And this camera is the more prosumer version. The one feature that's best in this is it doesn't matter whether you buy it in the States or you buy it in Europe. You can switch between 1080 50 frames per second, 50 iframes per second, or 60 iframes per second. And this means that if you're in Europe, you can switch to the higher frame rate. It still gives you the same 1440 pixels by 1080 times 3. So it's actually beautiful images that come out. And I know, because I've worked with this camera professionally for a good number of years, I know what it can do. And then how are you going to capture it? Well, you know what? You can capture it right there in the camera. So if everything else fails, you can capture it right in the camera. You can have it running off battery for like forever. And it has this outputs here. You have an S video. No, you don't use the S video. If you want to use the S video, you have to downsample the HD content to SD content, and then you can capture it on the S video. Why? Because the S video will only output 400 TV line resolutions. This is all a bit complicated stuff, but maybe. But for those that don't know, that's not getting you the resolution. You need the lead that goes in here. This is the component output, and that splits it out, and you can get the full 1920 by 1080. It's actually anamorphic. It's stretched on that 1440 to 1920 on the output there. And that's something to bear in mind, but it squishes it in the optics so that what you see on the 19 by whatever it is, 16 by 9 frame is the right pixel aspect when it comes to using it. And how would you capture that? Well, when I'm looking at you on this camera here, I have used a £20 HDMI capture card that plugs into USB 3. It's got a universal USB codec thing. You don't have to put any installers in, and you can plug it into your USB 3 on your PC, your laptop, whatever, Mac. And I've tried it on Mac and I've tried it on PC. And you can use the free open broadcaster software to capture as long as you like. As long as you like. At HD. So you can leave the camera there on the battery with a fixed focus, with your fixed aperture, with your fixed shutter time, with whatever ND filter you got in front. And you can capture and capture and capture, okay? And you have an ability to look through. You will have to make your window on your reactor big enough to look through, but it's a CCD. It's a CCD and it's 3 CCDs. Every pixel's a winner. I can't speak too highly of that. Okay, this is not a rolling shutter problem. Okay, now the videos, all of the videos you've looked at have all been 30 frames per second, and they've all been 1920 by 1080, except there tend to be Bayer pattern mashups. Okay, and they're probably encoding the hell out of them. If you have the component video coming into this capture card, and I'm going to show you. Let's switch back. There we go. So, and you've got audio video out there, so you can sync audio and video with your component, and you can do it with ridiculously cheap equipment. Ridiculously cheap equipment. What you're looking at here is the the TTR or whatever it is, header here going to composite video, don't even think about using composite video, and your left and right audio. Okay, and then if you have your breakout component output from the either the HVRZ1 or the FX1E, you can put the component into these three and the audio from here into here, and then this is your capture card with your HDMI. So your component goes in here, the audio goes in here, out the back you've got HDMI, which merges the component and the audio, and that gets encoded in here, comes in here, and it's just a nice USB feed. Okay, and so this can capture up to 60 frames a second, not relevant, but actually it can, this box here, this one you can see here, it actually upsamples I to P. So you actually get, it doubles the lines for each frame. And so you actually get 60 frames P being captured from the either the American Sony FX1 or the European or American HVR Z1. And so you can capture 60 frames a second, double the frame rate that we're looking at here. And if you don't have the component video cable, you can use this device here. So essentially what I've done here is I've walked you through some extremely nice VEGA videos that have been produced by Henk and David. And I have done my best to walk through the range of different things that were occurring in these videos. And these are some of the composite shots here where I've taken a bunch of frames and mashed them together. So maybe I'll just kill the text off that. So in this case, you've got spiraling. And this is quite interesting because right on the North Pole, as it were, you've got a straight line coming out here, literally straight, and it looks like it's spiraling. It looks like it's spiraling. It looks like it's spiraling. Here's our squiggle, and here's a line over here. Is this spiraling? I don't know. Is it spiraling? What do you think? Here, this is again a composite, and this is our prominence, but because it's merged a number of layers together, it's faded out the explosion there. But you can see that it starts down here, comes up here, comes round, and we've talked about that. In this shot too, is it this top? No, it's this one down here, is it? No, this one here. In this one, you can see this comet trail, which we talked about earlier. And these were observed by the Sapphire team and by Ken Shoulders. And this is this one where it kind of springs in and springs out. You can see how much material was moved here. And over here, you can see the ball lightning here. And you can see how, just as it did in Day's video, it tends to come out of the top hemisphere here. And it's interesting because these ball lightnings like to form hemispheres when they're on an anode, and most of the emissions come from the top hemisphere. Is that something to do with the fact that this is the anode and there's some electric field in there, and that is part and parcel of the magnetic structure and how this causes emissions? I don't know, but that's for another day. Okay, so if anyone wants to ask any questions, any clarifying things, I would be, I'll give a stab at answering them. I think for me, one of the nicest things is the fact that we might be witnessing alpha waves here, and that we might be creating some, how should we put this, flux loops in our reactors. And that for me is just it's just amazing, really. And these kink instabilities. I believe we are seeing kink instabilities. Here's some more kinkiness going on. So you've got your flux loop between here and here. And let's go to our, where's our kink instability? It's not there. It's okay. Cancel that one. Yeah. Yeah. So you can see very much so that how these things form and they fall apart. and so on. This paper is by helical kink instability in confined solar eruption, and this is a paper. Let's get rid of that. And the astrophysical journal 2016, and the DOI number is up here on the top right if you want to go and have a look at that. I will try and put all of these papers into an updated version of the newsletter, but you can see how it's talking through how this instability is forming from this flux loop and how it breaks down and so forth. So here we go, coming up and back. So this is just not a simple glowing ball. There's something more interesting going on in this reactor. Okay, so do you have any questions? Okay, so I hope that the Russian was Russian translation was intelligible for Russian speakers. I see that we might have a Russian speaker here. I'd be interested to know whether that worked for you. High speed, that's an excellent idea. High speed or two different camera angles would give you more data. It's just, that is a fantastic idea. Yes, I think maybe you could use one laptop and two of these Sony FX1s or the dual format equivalent with the capture cards, and you could capture two aspects synced, and that would be stunning, because you could do some 3D assessment on the motion. That is an absolutely brilliant idea. Of course, you'd need to have two holes orthogonal to each other, ideally, in the reactor, but I think that's an excellent suggestion. Really excellent. I mean, of course, it doubles the cost of the cameras, but fortunately, we're not talking about cameras that probably cost about 9,000 once you've got them together and working, for one. Okay. Yeah, a super high-speed camera would be cool. Yeah, and in fact, some of those very high-speed cameras are CCDs actually, but they are ridiculously expensive, and you don't necessarily get these effects all of the time. But the great thing is that I have to say the great thing is that this was first observed by Henk. And it has been repeated a number of times by David. And by choosing the right metals for your anode and your cathode, having the right morphologies, doping them, for instance, in the case of the tungsten, it assists by doping it with potassium carbonate, the potassium in there, of course. You can potentially accentuate the likelihood of observing these effects. And the fact that it's been observed across two different power systems with different AC waveforms, this means that I believe that this is a very repeatable thing that people can do. Okay, I'm going to drag this one down here because it's interesting to have there. Okay. Okay. Wow, there is literally so many things going on here. There's discussions. Okay, I'll go down to the end. If you've asked a question before, ask it again. And I'll try and answer them quickly. But I want to be out of here for 10. It is an hour past my curfew, but I'm past it anyway. So... if you've got a question, I'll try and answer it. I am very, very interested in your opinions of what may be going on here. I'm not saying that I've given the answer. I'm just saying I'm the first person to have a look, and I've identified from my expertise several artifacting issues with rolling shutter, with exposure time, and with the type of CCDs and the focus and camera movement things. All these things can be cleared up, which gives us higher quality data. That excellent suggestion to have two cameras so that we can have some sort of more spatial awareness of what's going on, because you know, if they're orthogonal to each other, one's doing X, Y, and the other one's doing Y, Z or something, you can understand where things are going much better. Okay, so I don't know if people missed it earlier. I said that for people that are willing to have it on the record that they accept that this is something that can kill them easily, both in terms of the immediate threat of working with certain chemicals or working with high voltage and dangerous levels of voltage and current combinations. If they are willing to go on the record, then depending on what side of the pond they're on, we have circuits that people can use. Now, there are circuits that are extremely similar that are already on YouTube, actually. That's the reality. And people are quite open about how they built it. But, you know, we're not in the litigation business. We're in the science business, and we don't want to get into that because someone goes ahead and damages themselves. And then, of course, there is this issue with strange radiation, but we're doing our best to advise the best ways to shield for that. That doesn't mean it's going to prevent any cancers. And I would like to have the cameras and operate things at a large distance. So dilution is the solution to pollution. Just keep yourself distant from it. Okay. What is the diameter of the anode? Typically, they're about anywhere from. Here's a selection. Let me change the camera here. So there we go. They're like 10, 15, 20 kind of mil there. So there's a selection of anodes here. This one was one of the first ones that was run with the tungsten in it, so you can see that there is a tungsten rods going through it, and it's just an M8 nut, I think, or an M10 M8 nut, something like that. That's that, and maybe if I switch camera, it's actually going to be better on the other one, because I can zoom in and get it in focus. Is it going to work? There we go. Let's see a better closer shot on that. And it's through running a semi-random kind of like guided random anodes like this that became very obvious that the plasma forms on certain surfaces, and that enables you to have a more focused research program. Okay. Haha! So we have, thanks to Bido, purchased a spectrum analyzer. Not for okay. So we have a full spectrum analyzer in America, but we also have a spectral analyzer for looking at the emissions from photon emissions. So where you are seeing great changes in the color of these explosions, that may be because of different elements being excited, and those elements may be being synthesized during these events. And so after, and I'm going to be using that in the supernova reactor to see if there are elemental shifts in those experiments. Once that is done, then I'll be sending that, and hopefully when travel is permitted, going to work with Henk on setting that all up at his, to try and see if we can observe changes. And probably if this technology is suitable and can do the job with the supernova reactor, try and get one for Dave as well, so that that there is more data being made available. Do you think the behavior of the squiggles or solitons are interaction between the photons and phonons? I think it's more interaction between charged clusters of matter and magnetic flux tubes, or phonons. Okay, so or all of the above. I quite like the idea of Alfvén waves, because you have a magnetic flux loop and you have some massive thing that's going left and right, trying to be restored. It's going in that direction, but it gets pulled back and it overshoots, and you get this oscillation around the magnetic flux line. The bright particles may be following the magnetic fields of the flux. Yeah, I'm pretty sure they are. And also the magnetic flux lines are collapsing in, and you can see that in the videos. You've got the squiggle, and then the squiggle moves out as you've got an explosion happening, which could be actually a pressure wave, and then it collapses in. So that it could be part pressure, it could be part magnetic field interaction. So there's a smorgasbord of things going on, which is why you need high quality visual data to analyze, to be able to understand what's going on. So, you know, all of the above. Nice, you're talking about remote viewing. I will talk about more of that in the future. And I don't know from a sort of like scientific point of view, but I know from my own experience, and I'll talk about examples throughout my life. Boson can go through each other, right? Yes, I would imagine they can. Yes, they should be able to. I mean, if these things, I believe, have a very small dimension, and so they're radiating energy because material's collapsing in, and so they physically look large. But the boson core, I've argued that, you know, a black hole isn't a singularity. It's actually the dimension of one alpha particle, because the alpha particle is what comes out of these things when you have the boson over, as it did in S.V. Adamenko and as it did in other people's work. So the alpha particles come out, but the alpha particle is a boson, and it's the tightest packing of those 4 nucleons in space, and then it's a boson, so they can occupy the same space-time over and over and over and over and over and over again. So it doesn't have infinitely small dimension, but it can have all the mass you can possibly imagine in the space of an alpha particle. And yeah, okay, so what was it was going through the anode, by the way, but when they're in the neutral state, supposedly evos can go through whatever. Although they always retain magnetism, and so if you have magnetic material, and I've discussed this a lot, and there's experimental evidence both from ourselves and from third parties like Ruitskev and et al. And others, that they can be attached to magnetic materials. In the case of Bogdanovich, he was showing that if he used high speed electrons coming out of a cyclotron, and then he fired that into a conversion target, let's say, I don't know, tungsten, and it comes, you get high energy waves, gamma rays or whatever coming out. These cause these birdie shaped quanta of strange radiation to be formed, these so-called, what I understand to be a pseudo-magnetic monopole. And in that paper from 2019, I think it was May 2019, Bogdanovich et al. From the Moscow Nuclear Physics Laboratory, they suggest that these are knocked off the faces of the magnet, and they by the gamma ray. And so and they actually discriminate that some of the electrons that go through and don't get absorbed by the conversion target, they get pulled away by a field, and the gamma rays can go through, and it's the gamma rays that are ripping the collected magnetic monopole structures off the surfaces of the magnets. That's what they argue. And so you have Uretskev observing the changing of the magnetic fine structure of iron 57 from exploding foils and pieces of iron 57 sheets at 0.7 of a meter away, with a north on one and a south on the other, and you get either side of the mean by doing that. And you also have the Perovskikov paper from 2011, where they are collecting these structures from the environment. They believe they're some type of photon, but they're collecting them from the environment by using 0.4 Tesla magnets underneath some normal water, and then use lasers to emit these same birdie-shaped structures that get exposed onto X-rays. Color change, the light that you get, for instance, the purple that you see is from argon. Just go and look at neon lights, and they particularly, like a sodium lamp puts out a very specific yellow light, and that's why street lights that prior to LED ones are very yellow, and they don't resolve colors. So if you go down a street that's only lit by street lights, you don't see reds and greens or whatever, because there's no red and green or whatever being emitted by the sodium light. And so different elements, but of course the heavier element you get, the more spectral lines you get, and also the more level of excitation of atoms. So if you have tungsten in your reactor, there's many spectral lines that come out, so you get a lot of white light. But the other thing is that exotic vacuum objects, when they are condensing matter, they appear to produce soft X-rays and UV, and the UV can then go on and do other things, and the X-rays can do Bremsstrahlung. And so there's a smorgasbord of things that can happen. Yeah, Corky, that's what I say. A black hole is an alpha particle. Or it might be, in the case of that's when it's in the sphere form, but when it's in the donut form, it's a ring. So, you know, it has no dimension. I would argue that it has the dimension of alpha particles. But there's more pressure in the sphere, I believe, because it is a singularity. It's a singularity that does have a dimension, but it's a singularity. Whereas the ring is the how should we put this? The ring is it produces the lighter elements, and the spot this from a sphere. When you get a boson over from that, you can produce all the heavy elements, and this is what you see when you get like neutron stars or supernova or whatever. That's where supposedly the heavy elements come from, and I believe it's everyone knew it. That's why I have a Ra on my wedding ring here. The Ra in the center there. The ring and the spot, they are the interesting structures. You're making some interesting comments there, Peter, and I would refer you back to Tesla's book on his production of the Tesla light bulb. And I hope to be able to replicate that as one of the stretch goals with John Hutchison's book, to do the first known replication of well, that I know of, an accurate replication of Nikola Tesla's light bulb, carbon button. In fact, I don't know if you know, but in that carbon button light bulb, firstly, when you understand what's going on, and I hope my work and the work of Henk and Dave and so forth is helping to demystify that. But the high frequency oscillation and it can cause ionization, but at some point it's going to allow synchronization, and because you're going to get electron bunching, and this will form coherence. And he either used carborundum, silicon carbide, the very first silicon carbide made, or some of the very first silicon carbide made, or he actually used tar, which he then removed all the vapors from and carbonized it, and into the tar he put diamond powder, and so you have this high. Anyway, I will talk about that when hopefully we come to look at possibility of replication of that. Yes, synthetic, i.e. nitrogen, crummy diamonds are the best electron field emission, and for my belief is that is why they are so effective in the Lion experiment. Yes, it's always Numatech prototypes. If you can gain control of EVOs, it's the way you perceive exotic vacuum objects. Are you saying that they are something that doesn't exist in nature, or is the vacuum that they produce within their structure not the same as the vacuum we normally exist within? What is the exotic vacuum object? It depends on which way you look at it. Now, I know Axel would say that the vacuum inside one of these coherent matter structures, an exotic vacuum object, the vacuum inside is different. And so it's an exotic vacuum object. But it's not just exotic vacuum objects, it's exotic vacuum objects. There are many forms that these take, but the basic structures are spheres and torus. Jason, I think it probably can be controlled. I think what would be interesting is, can you put some electric field plates in there, or ideally some focusable magnetic beam devices like you have with the work of Boyd Bushman. So you have kind of like an advanced form of the primer fields. They don't need to be as complicated as the primer fields, but they're basically the same thing as Boyd Bushman's patent. And you have an electromagnet at the back, and so you could pulse magnetic beams into the cell in some way. But you need to be careful, because a lot of, unless you're using samarium cobalt, which has got a high Curie temperature, most of the strongest magnets, for instance, neodymiums, the ND52s, they lose their magnetism about 70 degrees or 60 degrees or something very low. So it's better to use, let's say, samarium cobalt in those, and then electromagnet combined with it. What does each individual color represent? We would know when we were able to look at the spectral lines, and we're working in that direction. I think learner development is possible without public funding. I think it is. My experience, sadly, with universities is that there's always someone that's willing to poison the well for fear of reputation trap. I want to be wrong about that. I hope that the universities being involved with the Horizon 2020 projects, which, by the way, our organisation presented a number of years ago to the EU with a view of them supporting funding in this field, because we replicated Chelani, and Chelani is one of the major beneficiaries and the key technology in one of the two groups that are getting funded. But I'm disturbed by the approach that at least one group is taking, and you know, I've reached out to them, and it's like hitting a brick wall, and I don't know. I mean, you've always got to make your boss look good, I guess, and I don't know. I think certainly it's always been funded. Essentially, the vast majority of the stuff that's out there has been funded by people's own time, actually. I think this is something we got to do for ourselves, by the way. We just got to do it for ourselves. You can't keep waiting for someone else to solve problems. You guys out there watching this are very bright. I don't have all the answers. There's a lot of different types of instabilities in plasma, as I've shown in this video. Go and look at them. Look at the videos, which will be shared. Download them, study them, see what's going on, think what's going on, think what normal conventional explanations there could be, what already observed phenomena could be, how this relates to the scales at which we're talking, and how special it is that we're able to observe these at this scale. That sounds good on the diamonds. No, we'll be crowdfunding in several ways. We've always been crowdfunding. We've only been supported by the crowd and the actual people doing the experiments. And the reality is, a lot of these big budget projects, they're built around the budget, and everyone's getting, you know, whatever they need to live, and they're doing their 9 to 5 or whatever. And but sometimes these experiments, they can't just run on a working week. They need to run on odd time scales, like fully overnight for like a week or two. I think when the University of Missouri tried to replicate our GS 5.2 observations, they basically changed everything. It was so far from a replication, I didn't even know where to begin. But one of the most interesting things is that they changed the protocol so that they could try and start the experiment and finish the experiment in a working week and avoid working at nights. And it was like, well, that's not what we did. In terms of tubes, pneumatank prototypes, you will see some very, very interesting videos. Some things were seen early on, and this was expanded into a whole sequence of work, principally by Henk. And it's very, very, very interesting, and it will all be public. Peter, yes, it can be done as people work together. I believe it can be done. But we can't go and ask a university how to protect ourselves from EVOs because they haven't got a clue. They haven't got a clue. They'll just laugh you out of the room. They don't even want to look at the research that demonstrates what they can do and the fact that they exist. We've got to work with the observations we have. use best practice. I'm not ready to do what the Russians are doing, which is having mice in the room or different types of organisms exposed to the radiation, and that they are very proactive in that regard. But the great thing is that they're sharing those findings. Okay, so let's use the fact that they're sharing those findings and give back to them by doing what we can do. Gardi, from my point of view, I have just done experiments and watched other experimenters, and fortunately had the opportunity to be with them and have discussions, and they've said what they believed was the most important thing. And when you see enough of these things, it points into a direction. And it really wasn't until late 2016, pretty much after I had visited George Eagley in Budapest, and we had these videos called Stardust, which you can see on the MFMP channel, where he was talking about his ball lightning experiences, that I came across Ken's shoulders. And again, it wasn't until much after I'd observed many of the things that Ken had seen and that Matsumoto had seen that I even found out about Matsumoto, and that was in first half of October 2018. So it was a sequence of things. Hopefully, if people are looking at the work that the MFMP is doing and the contributors to it, and there are context out there, some of the stuff in the past is wrong, okay? And if people want to go on about what is wrong, then fine. Some of the stuff we're doing now might be wrong, but you know what? I could not walk, and then I could walk, and then I could not run, but then I could run. And I didn't hate myself because I couldn't run when I started. Learning is about progression, but you can avoid making the same mistakes and going down the same dead ends that we did. And you also have these openly shared material now to draw from and make your own observations. And for God's sake, share what you find out. Share with the other community that is working in this space. Because so many people are wasting life rediscovering the same old stuff, and they think they're doing something new. Most of this, as Piantelli told us, was worked out over 100 years ago. Over 100 years ago. As I said at the beginning of this, Langmuir in the 1910s, right? He discovered 7,000 times the volume of the mass of his tungsten filament in his tungsten light bulb. This gas was being produced, and it was so significant that he wanted to spend 5 years studying why, right? You have Barkla, who got awarded the Nobel Prize for discovering characteristic X-rays, exactly what we're talking about, to determine the elements that we find under an EDS. This guy, Barkla, found J radiation. Why J? Because it's inside a K. K is the inner shell. J radiation should be something even more inner because it's producing higher energy radiation. It's not nuclear level radiation. It's not gamma rays, but is higher than the highest X-ray you can get. And he found this in the 1910s also. And he spent the rest of his life trying to work out what J radiation was. J radiation, as far as the Russians are concerned, and as far I would agree with them, is strange radiation. It is this, and it's caused by the same kind of sequence of events. So most of this was discovered back then. Sadly, we had the First World War and the Second World War, and George Eagley goes on about this. A lot of people that could have solidified this understanding were killed off in these two world wars, and there was this dead space of you can't touch nuclear because of the bomb for like 60 years. You couldn't even go near it, and people weren't allowed to learn. But what we have now, the stuff you can get on eBay to image this and to build this, and you can go and get scrap magnetrons, okay? They are very dangerous, but you can go and get scrap magnetrons and build experiments out of literally stuff from the dump, just like John Hutchison did. These things were simply not possible The magnetron didn't even exist in the 1910s, 1920s, and even whatever. Like, it didn't even exist back for them to explore it. You couldn't just go and get a scrap high voltage transformer. It just wasn't possible. So we are in a luxurious zone now. And what you are seeing with these Vega experiments is a whole blue ocean of potential discovery. A whole blue ocean. And you can move fast like the Russians. The Russians don't care about how shiny their experiment is, how many millions or billions were spent on it, how many PhDs work on it. They care about, I do this, that happens. I do that, that happens. If I change these parameters, this other thing happens. Right? What are we observing? These are the things we observe. If this is dangerous, how do we know it's dangerous? Oh, now we know it's dangerous. How do we shield against it? They're not trying to spend a huge budget. They're trying to deliver the science. And this is actually what happened at the beginning of the last century. Somewhere in the middle, people got lost. And, people have to... I know. As I said, I sold my Sony FX1 to pay bills for a month. You have to make ends meet. That's true. But I think we can do a lot together. Yes, we can be wrong very, very quick. We can be wrong very, very quick. When I looked at these things, I got very excited because I thought it could be X, Y, and Z. But then these videos have so much going on in them, and you can learn so much from it. Yeah, just. What you're seeing, though, is things that are occurring in stars, and it's not like guesswork. People are saying that are published in recognized journals that these things are occurring in stars. Yes, they have to model them to be able to kind of... They're looking at something that happens on a star and say, like, what can be happening in the magnetic flux lines? And here you are. It's there. It's there. You're seeing a kink instability. And you see loads of them in this experiment. In my view. I'd like other opinions. Yeah, there is greed is the biggest protector of Lena, really. I think it's a combination of the unbelievability of it and greed, and also the fact that I'm utterly convinced since the beginning of 2017 that it's been weaponized, and it's just sad. Weaponized, and also there's other uses for it, like AG and stuff, and so because they are so significantly important strategically, they don't even want to get people close to understanding what's going on. Yes, Axel, I believe when you get a boson over, if you look at what we observed in echo fuel, but also the work of Matsumoto, when you have these boson overs, sometimes you get particles coming out, and sometimes you get a substructure of the EVO, or even what's left of the EVO, that reorganizes itself. So you get a range of different tracks and a range of different particles. And in fact, SV Adamenko, so you get basically everything and things you'd never seen before. But you can see in the video that I shared that there were things that came out of that star explosion, which there was nothing there before, and from a point in space, something blew up, right? So that, I believe, would be a self-compression of a black EVO. And you get the particles of different energies going out. So in one frame, you've got things traveling different distances from that single point of time. And then from that same point, you've got something that comes out which is curving, which is traveling down potentially its own magnetic field line, or it's caught itself onto the magnetic field of the nearby large macro ball lightning or exotic vacuum object. This is more possible to do. In fact, it's going to become impossible. I lament the fact that you can't go out and buy a tungsten light bulb now. I lament that we're going more and more to digital systems rather than analog. Remember, John Hutchison's work a lot of it was done with analog and valve, you know. So you are getting to a type of technology that is extremely susceptible, if it's not shielded in a way which is quite special, to being damaged by this technology. I was marveled at the difference between a Claymore mine, which cost a vast amount of money, and the mines that I learnt how to clear, that were made by peasants in the middle of Russia. You know, they would send 2 people to a training camp, and they would show how to make these mines out of wood, sticks, and basic explosives that would blow up a tank just as good as an anti-tank mine that cost a vast amount of money. You know, it's the whole approach to science. It's kind of like hypothesis, you know, experiment, observation. What does it tell you? Go back to our hypothesis, and you know, we can do that very fast if we're working together. No, I'm sure. Sorry, but yes. It is harder to isolate people, but you know, I've seen both within outside of the community and inside the community attempts to stovepipe or like channel people in a direction. I mean, um, and it's just spinning a plate until someone dies. That's it, because people's lives are short, and they'll take a paycheck rather than going in the direction that matters. It's our responsibility as a group community to say that this is not the right direction. But you know, when you look at what is being observed in these Vega experiments, the truth is what you see. I want to make it the whole truth by getting the right kind of imaging on the situation, because you know there's things that can be challenged because of the use of rolling shutter and partial frame exposure and stuff like that, which I discussed at length. So that these things are much more certain. But it's the truth that is in the action of the matter in the reactor. It's not, and then when you find, like when you observe these things wetting together, then you find that there's a 2001 Journal of Fusion Technology, Japanese paper that says these things wet together. And then when you say that they're coherent matter because it looks like they're coherent matter and they're able to disrupt things without disrupting something inside, and it's just this boundary layer, and then you get sent a book that says, oh, we believe that this is coherent matter and it's like, when you look, you think, and then you say, well, what could possibly be doing what I'm actually physically seeing reality do? Believe your eyes. Believe your eyes. Yeah, conscious energies, yeah. Don't expect to see the answer in your lifetime, but work with others that are like-minded. Not necessarily that aren't going to challenge you or come up with a better idea or new ideas, but that are like-minded in the ontological sense, that we want to get to an end point where we have the answer and we can use this technology for good. For good. I guess I'll close out with this. I could have walked away from this 100% at the end of February 2017. I had realized it had already been weaponized. Absolutely certainly. I recognized that most of the key aspects of this technology were established in the 1950s and the 1960s. I felt really, really annoyed that I'd been effectively wasting my time volunteering doing stuff which is already known. It's like you are consciously aware that you have been wasting your one life. But what I realized is that if I walk away from this now, I've really, really wasted it. I had to think, okay, it's been weaponized. Some people know this, but do we only want those that have it and can use it against us, or to subjugate us, or to pull off some party tricks? Or do we want to have all of humanity recognizing this technology, as I believe we've already done in the past, our species, recognizing this technology for what it is, what it can do, and then coming together as humanity and ensuring that the positive aspects are used. The positive aspects are used. And so I recognized in 2017 I would face ridicule, humiliation. Fortunately, I didn't have a scientific reputation I could destroy only within the community. But it didn't matter. It does not matter. It does not matter. It's the truth that matters. The truth is what you see in these images. Now, what could be causing them? Could be mundane things, okay? But we need to get to the bottom of that. But sooner or later, we're going to understand what it is that's causing the coherent matter to form, and so on. I've got a lot more to say on that. It takes time and energy, but thank you for your time tonight, really. And hopefully you can understand the difference between this image, and this image, okay? And what I'm saying is, one is a representation of the truth, and one is far closer to reality. And we need to up our game in terms of the quality of the images, but we don't need to do it necessarily with stupid expensive equipment, because there is a lot of people chasing a few extra pixels and a few faster frame rate when they're not necessarily the best thing for the job. And I hope that the experience that I've had through my professional career in understanding imaging technology that I've shared with you tonight, I've showed you the only option which is practically available to researchers out there, which is actually really rather cheap. In fact, what I showed you, like a whole camera capture system, if you've already got a computer, effectively is cheaper than one lens for that other camera, and even cheaper than many lenses for a normal SLR or mirrorless camera. So, you know, we can have multiple of them. That's been an excellent suggestion. Okay, I do need to go. I only had a small sandwich for my supper. I've been working all day to make sure I could do the best job I could, because it deserved it. What Hank and Dave have done deserved really thinking about what possibly could be going on. And please engage with remoteview.icu. Ask the questions, propose papers, look at the videos. I'll try and get these 3 core videos up and put them into the blog after I've eaten something. Download them. Use 4K downloader. Download them. I might even give a link to the raw footage for these 3 videos so that you can study them in depth, pick out things, onion skin some things together, and try and understand what's going on relative to whatever else is going on in the cell. Okay, thanks guys. I will see you soon, and I want to get more onto talking about coherence. I have a fun blog that I'm going to put behind the paywall. It's only about personal stuff on remoteview.icu. Thank you very much for the people that are supporting me with there. That helps me justify the work I do. Thank you particularly to Bido and Show in recent months and in years. That's helped me de-stress my presentations so that I can focus on the content rather than fumbling around trying to switch views or whatever. So at some point I will talk about the really affordable system that I've put together here for sharing information, and I think this will be a fantastic tool or group of tools to be able to share live experiments in a way that's very compelling for people as we move forward. So with that, I'll say thank you very much, and sayonara, good night.